Hi, everybody, and welcome. Today we're in May already, May 4th. We still have about basically 4 weeks of lecturing. We have quite a few materials to cover, okay? That's why you will see a little bit of, how should I say, like two concepts together. For example, today we're going to do chapters 25 and 26. And if you look closely to them, one of them has to do with the electromagnetic induction, and the other one with the EM waves, basically, okay?
Does that mean we get a whole week of review before the final?
We have, yes, we have about, yeah, so when you consider that, let me look exactly into in terms of how much material we still have to cover. Hold on. Okay, so models. So today we're doing 25, 26. This Thursday we're doing 27, 28. Then next week we're going to do 29, 30 plus 31, 32. And we get into, so that's quantum mechanics. And then we get into atomic physics and radioactivity, special theory of relativity. Yeah, that's basically a lot of material. Yes. So according to this, it's planned to, by May 31st, we would be done, okay? No, you will have about, usually it's not exactly a full week, it's about 5 days basically of review, okay? But you will have plenty of review. So it's really not a final in the sense that you only are responsible for the content of the chapters past the first exam. So it's only half basically content. It's not a comprehensive exam, okay? The final for this class is structured differently than some other classes that I do. So that is in terms of basically where we stand on this thing. So so let's go back into the topic today. Let me do something. I'm going to switch cameras, okay? Because I'm going to do a demonstration of the concept that we need today. And what I have in here, I have a multimeter. I also have a coil, basically, which is a bunch of wires basically made into like loops, okay? So there are so many of them condensed into this packets in here. This material is non-magnetic. As a matter of fact, if I try to bring a magnet and attach to it, it won't stick, just to show you that it's not magnetic, okay? So the point being in here is there is no magnet, but I will still need a magnet in here, okay? So I have this bar magnet, and that's all we need. So I'm gonna switch cameras. Before I do that, I need to turn on the light, because apparently I need to have the light going at an angle because the other camera is going in. So basically I need to change the light direction of the light. So hold on a second, okay? Let me change cameras and let me turn on the light to demonstrate Faraday's law. Hopefully you guys can clearly see some of the stuff that I have on the desk. And here, this is stuff that I was showing you. There is the coil. There is a wire that is connected to it. For some reason, it's not. Yeah, I think it's because of the light. Here is my bar magnet. I'm gonna put it in here. Actually, it's a mini bar magnet to give it a little bit of strength. That's all. Here they are. Okay. And there's another magnet in here, which I don't really need. This one is not needed for this purpose at all. This iron filings are not needed. So what I need in here is this multimeter. The multimeter, as you can clearly see, the COM port is connected to the COM port, and now this one, the red one, the red lead basically to it, which is in here, is connected to the where it says milliamps or microamp, meaning tiny currents, okay? If I want to measure high currents, I have to put it in the 10 amps because I know that this is going to be a super weak effect. So what I'm going to do, I'm going to connect it instead to the milliamp to see how much current is flowing through the wire. Right now, it's not on, so I need to turn it on. Right now, it's telling me basically a reading, if you can see, hopefully, let me move this out of the way here. A reading of 0 current. Let me stop it in here. A reading of a 0 current, okay? As you can clearly see, there is no current in the wire. So basically the wire that leaves, doesn't matter where you start from because it's just a wire. There is no battery basically. That's the main thing. So there is a wire in here that is connected to this end, goes around, comes back to the to this end of the multimeter, and from here it's going to come out from the other side. It comes out in here from there, and then it closes. So there is no current basically. What I'm going to do now, I'm going to take a magnet and put it on top of this. There is no magnet still, but if I move it around, as you probably have seen, if I move it out or in, while I'm moving it, there is actually a current, and you can see the readings on there, and it's being registered. So if I stop this motion, there is no current. If I stop it, as a matter of fact, in any position, the only way you're reading something in here is because my hand is really shaking, but now I got it, okay? But if I move my hand anywhere in and out, there should be a current, okay? That's one way of getting a current. How about if I do it the other way around? I'm gonna put this one sitting still. Is there a magnet in here or something? Okay, it looks like this thing has a magnet already in it. So the same thing, if I put it sitting still, I should not really see any current. Right now, the only reason is because my hand is shaking. But if I move it in and out, again, I'm registering current. And if you can clearly see on this side and here, there is a sign that keeps on changing from positive to negative, depending if I'm taking the magnet in or out, or in this case, the loop in or out, or a bunch of loops in and out. So this is, in a sense, Faraday lens law. So this is Faraday lens law. So let me switch cameras. So we were at some points in the early 1800s, we knew about Ampere's law that the currents create magnetic field. So Faraday and other people were interested in the other way around. Could a magnetic field create a current? And the answer is yes. It has to be changing with time, though. As a matter of fact, more precisely, its flux needs to be time dependent, needs to be changing with time. So that was really what's going on in here. Because if I take this magnet, I still have my stuff in there, and move it somewhere else, or move it in a fashion where there is no overlap in the between the magnet and the loop. If there is no overlap, no matter how much this magnetic field is changing, it's not going to impact the. There will be no current registered by the multimeter. So in a sense, that's basically how this law is. So let me share with you the screen. Share. So we're going to talk about the electromagnetic induction, and that is Faraday. We call it actually Faraday lens law because the way that Faraday posted it, or at least stated it, did not really fit the bill 100%. In a sense, there was a sign issue with it. So Lenz came in and fixed the sign, and the sign is critical. It tells you not only there is a current, but tell you which way the current is flowing. And that's critical if you want to build devices and everything. You don't just want to know if there is a current, you would want, and how strong is the current. You would want also the current, which way is moving, which way is going. Hence, it's called actually Faraday lens law. So probably I should fix it in here, and it's called Faraday lens law. Okay, and it's the idea behind how electricity is generated, because you can clearly see in the experiment that I have shown you, there was absolutely no battery whatsoever. I don't have a battery in the circuit, yet there was current, and the multimeter picked it up. I cannot really put a light bulb in there because the current was of the order of 10, maybe 100 microamps, and this is too weak of a current to register light, for example, to trigger, to heat the tungsten filaments inside the light bulb, for example, like this one I have in here, to see actually to heat so that you will have an actual current in it. You will see it actually light up. So it's not going to be that strong of a current, at least the way that I'm doing it. But if I'm doing it super fast, like for example, I don't know if you're familiar with this concept. There was a dynamo in the old days. I don't know. I think they still sell it too. You can go on Amazon and find it, where you can attach to the wheel of the bicycle, and then while the bicycle is moving, can generate a current, and that current can actually light the light bulb of the bicycle, and you can have light. Obviously, for a light coming from the pedaling of the bicycle, the light will be flickering because it depends on how fast the person is moving. The faster you move, the brighter the light. The slower you move, or if you come to a standstill, there will be no light. So that's the idea behind it. So again, that is how current is generated. I mean, the current that is delivered to your home or to your business of work, it has to go through this process, through Faraday's law. You have a waterfall, at least in the waterfall near Hoover Dam, for example. As the water falls, it turns a turbine, and that turbine is basically what it is you have a big magnet like the magnet that I have in here sitting inside a coil. As a matter of fact, it's no different, honestly, than the motor that I have shown last time, except the process is reversed. So basically, all you have to do is find a way to turn this one. So there is a current. If I can harness that current now from this leads, if I can harness it, there is that current that is actually right now is being generated as long as I'm moving this one in here. So I have a coils moving inside the magnet. So a motor and an electric motor and a generator are just the same idea, except they work reverse upon another. So in terms of components, they're similar. Okay. So that is basically how the power is produced. And then there is another concept, which is a concept of self-induction. Let me show you a circuit in here. Okay. This circuit, yeah, stop sharing so that you get a better view of it. What I have in here, I have a bunch of electronics in here. These are capacitors. There is another capacitor. There are some resistors. There is some transistors actually in here, and some other nonlinear electronics. But what I want to bring your attention to is this. What looks like it's coils in here. There is one. There is two in here. There is another one in here. And there might, oops, can I remove this? There is this one, basically, I was trying to show you. And there is one in here. It's hidden behind the capacitor. There is this one, as I was showing. There is one in here. It's hidden behind the other capacitor. And there are two next to my finger in here, okay? So there are a bunch of them, and the reason why I have a bunch of them in here is because this is actually an oscillator circuit. This circuit is actually for telecommunications. You send and receive signals, and you interpret signals, and you go through modulations and get rid of different frequencies and things like that. How would I know that? Look at this thing in here. That is actually part of an antenna lead that comes in here. So that's how you connect it and grab signal. And if you look carefully to this thing, that is actually the HDMI. So this is supposed to send a signal to a receiver like a TV or something like that. This is actually USB, plain USB. So this device, this is the power supply. This is where you connect the power supply to it. So this device is some sort of a telecommunications, and it uses this inductor. So let me go back into the screen in here. So this is the induction. So the induction is this coil that you saw in the circuit, and it's made up of those tiny things that are going in circles. You have another kind of induction, which is actually very useful in circuitry also. Like, for example, this one. This is actually a transformer. You need induction in transformers, and usually you have a primary and secondary. You have the primary inducing a current in the secondary, and this is really how this works. So this is the principle behind a transformer. Transformers are essential in power distribution. Without them, you cannot really deliver power to any point. Obviously, this is, I took it from an electronic device. Again, as you can see, there are 4 legs to it, 2 legs in the primary and 2 legs in the secondary. Which one is the primary, which is the secondary? It doesn't matter. The primary can play the role of a secondary, and secondary can play the role of the primary, and the transformer can be, instead of being a step-down transformer, becomes a step-up transformer, and that's all. Okay, or vice versa. Okay, so I'm calling this as primary. I'm calling this one, the 2 leads in here, as secondary. It could have been the other way around, and that's irrelevant here. So again, this is part of the power distribution and power consumption. Usually, you need transformers because the power company that is delivered to your household, at least while into the wall, it's reading 120 volt. Okay, 120 volt would be too much for your phone. Oops, my phone almost. Yeah, it would be too much for your phone. Your phone probably requires only a few volts. So you need to bring down the voltage from 120 down to like 5 volts or something. So you need a transformer. Is this a step-up transformer or step-down transformer? When you bring 120 volt to 5 volts. It's step down or step up? What do you guys think?
It's step down, right?
It is step down, yes, because you bring the voltage down from a very high voltage down to lower voltage. As a matter of fact, if you go outside of your house or where you live, you will see big transformers in your neighborhood that actually the power company, when it delivers power to your area, they deliver extremely high voltage, but you need to bring it down to a more manageable voltage so that when it comes to your house, it becomes manageable. So there are a bunch of step down transformers, but near the power company, where the production of the power is, they really need to bring it to a high voltage so that they deliver it on those power lines, and the power lines actually carry that high voltage. So there are step-up transformers. Most of the times, consumer transformers, 99% of the times, they're actually step-down transformers. But the same step-down transformer can actually play the role backward and become a step-up transformer. So that is, let's go back into the slides in here. So all of this has to do with this idea in here. Again, the second topic in here, look, around the 1850s, 1860s, and especially around 1870s, Mr. Maxwell looked at all of the laws of electricity and magnetism and tried to put them together in just one big law. He had Coulomb's law, which can be expressed in terms of the electric field. So he has a law for the electric field. He stated that law. He had a law for the magnetic field also, on how the magnetic field diverges. It doesn't diverge, it goes around in circles, basically. So that was the second law, also for the flux of the magnetic field being zero because there were no monopoles. Okay, we talked about that last time. And also, he looked at the law that how the magnetic field is created by the current, and that turns out to be Ampere's law. So Ampere's law explains how magnetic field is created by how the electric field is created. I mean, how the magnetic field is created by current, and the current is actually created by the electric field indirectly. So in a sense, in order for me to have a current, I have to have a voltage. You have a voltage, and the voltage is really due to an electric field. So the electric field creates a current, the current creates a magnetic field. So in a sense, what we have with Ampere's law is that an electric field creating a magnetic field. This is what prompts actually Faraday to do this experiment and come up with can I make up an electric field out of a magnetic field? And the answer is yes and no. Yes, if you are careful enough and change the flux of the magnetic field. Turns out the flux of the magnetic field, when you change it with time, creates a current which can be interpreted as that due to an induced electric field. So that was the fourth law, the fourth basically equations that he wrote. There was something the matter with Ampere's law he didn't like very much, so he had to modify to account for phenomenon that the Ampere's law could not account for. So when he did that, that law, instead of being called Ampere's law, nowadays known as Ampere-Maxwell's law. So you have these four equations that Maxwell put together. And he said, you know what? Let me look at these laws in vacuum. Let me try to see if I can solve these equations in vacuum, meaning far away from electric charges, far away from currents. How is this law going to be? It gave him something which was a solution, which was waves. So the electric field and the magnetic field were going in a wave, okay? And they have to exist together. You cannot have the electric field by itself and the magnetic field by itself, because if the other one is not there, both of them are not there. So it's an all or nothing, basically, game when it comes to this Maxwell's equations. So it has to be then an electromagnetic wave. It cannot be an electric wave separate from a magnetic wave. Both of them are the same thing. In a sense, they work together. It's like you take a coin, and I know I have a coin in here somewhere. Yeah. It's like you have a coin, and you look at the coin. From one side, it looks heads. From the other side, it looks tail. That is exactly what's going on between the electric field and the magnetic field, that they are two sides of one thing, and both things are called now the electromagnetic wave. Not only that, one of the immediate conclusions of his work is that the speed with which this wave is traveling is exactly the speed of light. Could it be that light is an electromagnetic wave? That was really what he arrived at. And it turns out that his solution gave us light, the visible light that we use, basically the entire spectrum of light from red all the way to violet. But then it gave us something outside of those regions because the frequency was really not bound to the region of the visible light. So we had extremely high frequencies like the ultraviolet lights, like the X-ray lights, the gamma rays. And then we have even less frequency lights, like, for example, the infrared light, the microwave lights, the radio waves. All of them, they have the same behavior. They travel with the same speed, namely the speed of light. So that is basically what emerged from this whole work on electricity and magnetism. That was the grand unification of electricity and magnetism and optics also. Because before that, Young in the early 1800s conducted experiments involving light, and he found out that light behaves like a wave. He didn't know what was waving. But definitely it has a wavelength, and he was able to find what that wavelength was. Okay, he didn't know what the frequency would be because he didn't know how fast light was traveling at that time. There were some experiments how fast light travels, but if we know how fast light travels, and then if light is really a wave, then we can find its frequency. Hey, listen, we can, to the time of Young, we can assert it's a wave, we can find its wavelength, we can find its frequency, but we had no idea what was waving. Up until the time of Mr. Maxwell's solutions, then we knew what was waving. We knew it was the electric field and the magnetic field, both of them working together to basically do this thing, these oscillations. Obviously, this was a big departure from the old idea of light being made up of tiny particles that Mr. Newton has formulated in order to explain the laws of reflection and refraction. But that's because that assumed that light is made up of tiny particles, and those tiny particles are moving a line until they hit an obstacle, then they bounce off, just like a tennis ball. And that explains the laws of reflection and refraction. But then came this work of Mr. Young, and later on, basically the theory of Mr. Maxwell for the electromagnetic radiation that completely decimated that. So we had to understand again reflection and refraction in light of what's happened. Because if light is not a particle, how can we explain the laws of reflection and refraction? For that, Mr. Huygens came up with a principle that basically like a compromise to fix that. And that, of course, was until the late of the 1800s, when Mr. Einstein came up with a theory to explain the photoelectric effect. And that says that, wait a minute, Newton said light is particles. And reflection and refraction prove that. Young showed that it's actually a wave. He didn't know what was waving, but he can definitely determine its wave patterns because it does interference. Mr. Maxwell showed exactly what was waving, namely the electric field and the magnetic field. But the photoelectric effect cannot be explained by a wave. It has to be explained by a particle. So Mr. Einstein proposed the idea that light is made up of tiny particles called photons. So what is light then? Is it a particle or is it a wave? Does anybody know the answer to this question?
Both.
Very good. So that is actually the item that I want you to really take from this today's light discussion, is that light can behave as a wave. If you do it, for example, in the double slit experiment for Mr. Young, it is a wave. Because you can do an experiment and find its wavelength and find its frequency, and there is no problem with that. If you look at it in terms of the electromagnetic spectrum, it is a wave. It has a wavelength, it has a frequency, and it does interference. That is, only waves can do that. Nobody else can do that, okay? If you look at it, for example, in terms of the photoelectric effect, the thing that some people have on their households, a house, for example, where they put those photocells on their house to generate power, that requires light to be a particle made up of photons. So light can behave as a particle when it wants to.
You mean to be sharing your screen?
I'm not sharing the screen, yes. I'm not sharing the screen. I'm just discussing it. Light can behave as a wave if it needs to, and light can behave as a particle if it needs to. Okay, so that is the point that I want to come to, that you guys will take from here. And of course, we're going to continue this discussion later on. What happened with Mr. de Broglie, who suggested something else about particles, that particles are actually waves too. So that is actually the revolution, the quantum mechanical revolution. So again, let's get into a little bit of stuff in here. So this is an experiment. I showed you guys how it works. Actually, this experiment has a wire, has a turns in here. Henry also worked separately on this work. Okay, so last sometimes it's called by Henry too. So they worked on it separately, and it's one of them in Britain and the other one here in the United States. So if you put a galvanometer, like the one I showed in here, when an ammeter is detecting tiny currents, it's called the galvanometer. That's basically the same thing. And like the device I have, a multimeter that I have in here, can work both as a regular ammeter or as a galvanometer. If you put it there and you vary the magnet in and out, you will detect that there is a voltage in here, there is a current in here. So this is exactly, so there is a slow motion produces hardly any voltage. So if you have no motion at all, you have no voltage. But rapid motion creates a rapid current. And the same thing, whether it's the magnet is moving or the wire is moving, as I showed in the demo. So you still have magnetic. There is actually a third thing that I couldn't show, and I cannot show it, and that is if I keep the wire in place, not move it. And if I keep the magnet in place and don't move it, both of them are fixed, but change the strength of the magnetic field. If somehow I can manage to do that, that too will create will induce a current. So that too. So what matters really is not the fact that they move with respect to one another and the overlap area is changing, but it's really what matters is just the fact that there is a time dependence for the change of quantity we call the flux of the magnetic field. How many field lines are going in over a surface? If that number changes due to the motion of one or the other, or due to the fact that the magnetic field is getting stronger or getting weaker, then in this case, that will induce an EMF, an electromotive force, or a voltage. And you can see it with your voltmeter or multimeter. So again, this is the law, states that the induced voltage in a coil is proportional to the number of loops multiplied by the rate at which the magnetic field changes within the loops. So again, the reason why I have so many turns in here, if I did not have them, this would have been, if I only have one turn, it would have been extremely weak current, is to amplify the effect in here. So I have so many turns in here to amplify the effect. So the number of turns matters to get stronger and stronger currents. So amount of current produced by the element is dependent on the resistance of the coil, of course it is, circuit that connects it, and the induced voltage. Sorry about that, okay? Let me get this in front of my mouse so I can put. Okay. So, and this is actually a resistive effect. I have a video where the eddies form, and the eddies basically is, look, if you have a magnet moving inside a conductor, okay? Doesn't matter which conductor that I have. It's going to induce, leading to it a current that is going to slow the magnet, and dragging behind it actually a force that is going to slow it down. So this leads to like a friction actually, and that is going to be harder and harder to do. If you keep on doing it, it's really going to be hard because you have to fight those magnetic forces, okay? Because you're pushing against an induced current, and that induced current will create its own magnetic field, which opposes the changes in the flux that you're moving in, this magnetic field that's going up and down. Okay, so of course the repulsion is due, the resistance is due to the repulsion between the magnets, the induced magnet and the actual magnet. So these are basically the way that you get voltage induced in a wire requires changing of the field lines, moving the loops near the magnet, moving the magnet near a loop, changing the current in a loop in a nearby loop. So in other words, if you have a nearby loop that has its own magnetic field, that is what an electromagnet is, and you have a loop in here sitting by itself. So if you change the current in this loop, the magnetic field will change. So you don't move anything, and that will lead to actually current in the secondary. This is the principle of the transformer. So what's going on in the transformer? You have two loops, one next to one another. Let me stop sharing quickly. So what's going on in a transformer? You have two loops. This one is next to the other one. So you have the top one and the bottom one. So if the current changes in this, okay, if the current is time varying, for example, an alternating current, this will mean that the magnetic field that it's creating is also changing, which will cause the second one to have a current in it that is going to also be a changing alternating current. That is how the transformer works. So a transformer, you have two separate basically coils, and the coils are completely separate from one another. But one of them can induce a current in the secondary. So the primary can induce a current in the secondary if the current in the primary changes. That's why transformer requires an AC current. Transformer does not work with a DC current, because if the current is fixed, doesn't change, well, in this case, there will be no current in the secondary no matter what. As long as, because the area is not changing, the magnets are not moving, and the current is fixed. So the flux in this case, there is a magnetic field though, but that magnetic field is not changing, so who cares? So you really need to have an AC current in order for you to have for transformer to work. Transformers do not work without AC currents. But again, to go back into an electronic device, whether it's being your laptop or your phone or your computer or your TV, they really don't use AC current, they use DC current. So the power company delivers the power in an AC current, and somehow inside the circuitry, usually near the power supply, there are regulators that they take an AC current and brings it to a DC current so that it's consumed by the device that you have before you, okay? Or sometimes for the phone, especially in the plug itself that you plug to the wall, and then there is a lead current. So the current that is coming from it is actually already DC current to charge the phone, okay? So application activation of traffic lights. So when you come to a standstill and light, for example, and there are a major highway where the light is always green to it, and you come from a secondary, for example, road that is all the time is red, except if there is a car in there. So what's going on in this case is the car comes in, and it's mainly metal, the car. There's a lot of metal in it. So what's going on inside underneath the ground, there is actually current, albeit a very weak current going around inside that region. Because now the metal goes in, and there is a magnet in there actually. There is a current that is super weak going in. The minute the metal goes in, it's going to change the permeability of the magnet in the loop. And that permeability of the magnet will change the current, will change, I'm sorry, the magnetic field. So the flux of the magnetic field changes, and the circuitry detects that. They detect that, hey, listen, there is a change in the magnetic field. So now there must be a car above us or truck or something. So now triggers the electronic circuitry to tell the light, hey, you can go now on the sequence. So it goes yellow for the main highway, and then it goes red, and then you get the green light. And then after that, it's going to turn to the way it is. So that is used in there too, okay? For security systems in airports, they too have usually a current going around, and they run it through the person. And if there is a metal, and that metal will actually interact with the magnetic field in there, changing its permeability again, and that will tell them the current has changed, and there is an alarm that goes on saying that, hey, there is a metal here, okay? So it's used for metal detection, scanning of magnetic strips on the back of a card. So when you swipe it up, the magnetic field in there will interact with the circuitry and will transform a specific signal, actually, depending on the panels that you have in there, to the credit card machine. recording sound on a tape also, because the tape is actually the same thing here. It's just basically you're rearranging the magnetic field on it. Electronic devices, hard drives, and it's actually for recording and for data storage and data retrieval, using actually magnetic devices. Okay, how are we doing on time, man? We have a lot of slides, okay? And I know we probably need to pick up a little bit of speed. Again, this is the generator. So the generator is the opposite of a motor. So I showed you earlier, guys, how the motor works. As long as you have a magnet, you have a coil actually in this one. And the coil is, why is this flat? Oh man, I must have a circuit in here closed. Sorry guys, it's going to have fire in here, so I need to. Batteries are extremely hot because there was a sorry about that. Anyway, the point being in here is you have a loop. In the picture, you only have a loop in the, but you have a bunch of loops in here moving inside the magnet, and that is how electricity is produced. There are these brushes in here that you typically see in a motor and also in a generator, and the brushes are actually, you can see them, they're sitting right here next to where the pan is. Okay, this plate that is going up and down, and when you move this one, and there is actually discontinuity in there, every cycle it goes once on each side. Okay, so the current that you generate is going to be an AC current because it's changing in here. Its projection is going to be an AC current. This is a cosine function. And you can have wind in here to cause the motion, the mechanical motion, and the mechanical motion is translated again into it. So you have to have this one moving by one way or the other. Either move it by hand or by wind or by water falling in or by pedaling, basically. So whatever it is, this is basically, you have to have that in order to generate the AC currents. So the magnetohydrodynamic generator they use actually, it can make the magnet move up and down without having to have that spinning thing, that spinning motion, okay, the turbines. So this is the idea of transformer. I explained it earlier. So you have a power source in here coming from the primary, and you have power generated in the secondary just because the flux of the magnetic field in here is changing. The field lines are changing. More and more field lines are going in, or less and less field lines are going in, and that depends on the current in here has to be changing. It cannot work with a DC current. It has to be an AC current. So this is a representation of the transformer. If I take this one and put it in here and make this one the power source, it still works, except if the number of turns in here. Let's say, for example, the number of turns was 100 turns in here, and now I only have 10. So 100 turns in here, the voltage across them versus 10, the voltage is going to be less in here by that ratio, a factor of 10 to 1. So this will be step-down transformer, and vice versa is going to be step-up transformer. Okay, if you reverse the polarity, reverse the function. So this is, again, the same idea behind the transformer. Transformers do not really, yes, they make the voltage higher, but the current will go down so that the power consumption at the end will be the same, because you cannot create power out of nothing. That's basic thermodynamics law. So this is a different representation of the same principle. Again, I mentioned the step-up transformer produces a greater voltage in the secondary than supplied by the transformer. Secondary has more turns in coil than the primary. So if you have 100 coils in the secondary and only 10 coils in the primary, then it's a step-up transformer, and vice versa, okay? So a step-down. Step-down is the main transformer that you will find in the industry, though. Here is the main relationship that you're going to see, okay? The primary voltage over the number of turns is equal to the secondary voltage over the number of turns, and that is because the energy is conserved. Or at best is conserved, okay? So the voltage times current in the primary is equal to the voltage times current in the secondary, and that is power in the primary is equal to power in the secondary. So this is a transformer you might see outside of where you live. It's near the power line. Okay, it's taking a huge voltage from the power line and bringing it down to different smaller voltage. Self-induction, I meant it's like a transformer. Basically, you have a primary feeding the secondary, but the self-induction, you have a primary and only primary feeding itself. So that is the coil as I was showing earlier in the electrical signal. So basically, you have turns in here, and as the current changes in them, they oppose that change with the same rate, basically, which is just the change in the flux. So this is called the self-induction. Okay, so self-induction is real, and that's exactly how a lot of oscillators are built. Again, power transmission, we talked about this. This is the power production. Usually there is a step-up transformer, and step-up transformer goes through distribution points. And in here, it goes to smaller neighborhoods until it gets smaller voltages. And when it comes down to here, you probably have small transformer to bring the voltage down to consumable voltage. So that is basically the whole point of it. Power is generated at 25,000 volts or less and is stepped up. So you need a step-up transformer to bring it to 750,000 volts for long distance transmission. However, when it needs to be used, it needs to be brought down to 440 volts. No, when it comes in to about 440, but it needs to be brought down to 240 to 120 volts. The rest of the world is 240. We use 120 volts in the United States, but even nowadays, what is delivered to your household is actually 240 volts, and that is actually split when it comes to your panel inside the house, so that you're only using half of it, which is 120 volts for most devices. But some devices, for example, that the washer and dryer or some of the heavy equipment that require a lot of voltage, so you need to have two junctions in it to get the 240 volts. So you still have 240 volts, even though we are rated at 120 volts. So Faraday's law is the so this is actually not, this is Maxwell and Ampere's law. Okay. The only trouble with this is, like I said, Ampere's law by itself does not fit the bill. You needed something in here, and Ampere's law says a current creates a magnetic field. This one says actually time-changing magnetic field, time-changing electric field creates also a magnetic field. So this is, in a sense, the equivalent of Faraday's law, except for the opposite for Faraday's law, basically. A time-changing electric field creates a magnetic field. A time-changing magnetic field creates an electric field. So this is how it's going then. Let me get my pen in here. So a magnetic field, the symbol for a magnetic field is B. B creates an E. That is this guy. This is Faraday. Maxwell says E creates a B. That is Maxwell. So what you have in this case is you have both laws working together to actually help one another. So in the place where there is no electric field or magnetic, there is no electric charges or currents, you could have an electric field causing the magnetic field to exist, and the magnetic field, when it exists, causing the electric field to exist, and the electric field is now.
Ceremony.
Sorry? Anybody speaking? Did anybody say something?
I think it was an accident.
Okay, no problem. So this is what's going on in a region when there is no magnetic field, in a sense. So an electric field will create a magnetic field. The magnetic field will create an electric field, the electric field. And you see how this is going. So you start somewhere from a star, for example, or the sun, and this electromagnetic wave will make its way all the way to us here. Looking at it, obviously the distances are huge, although it's traveling with the speed of light, which is 300,000 kilometers per second. It takes, the closest star, it takes about 4.4 years for this to reach us so that we can see it. For further away stars, it takes even more. For the sun, it takes about 8 minutes. So this is, in a sense, the second part of this chapter, the second part of this today's lecture, okay? So this is actually the electromagnetic wave. As long as you have charges in here, and these charges are moving in and out, so they create now an electric field because they're charges, and they create a magnetic field because they're moving. Now, far removed from them, this phenomenon will be self-sustained. You don't need any more charges doing that. So an antenna, which creates an electromagnetic wave, needs the charges to move so that it creates an electric field and magnetic field. If it creates an electric field by being sitting still, it's not going to do anything because that's not going to create a wave. So what you need in this case, you need both to be generated. Once they are done, once they are created, then they don't need the source. They can live without it forever and ever and ever. Okay? Albeit their intensity drops. And that's what you see, for example, if you move away from a light source, the intensity drops. As a matter of fact, if you move far away, probably you will not see anything, especially at night. But it's still there. So the electromagnetic field is still there. So this is, in a sense, this is what I was describing earlier. Both of them need one another to exist. So the red one is the electric field, the blue one is the magnetic field. Notice that both of them are perpendicular to the direction of travel. So if this, let me see how I'm going to do this one. So if this is the electric field, so the electric field could be the x-axis. So this is the x-axis, this is the y-axis. The direction of propagation is perpendicular to both of them. So this is traveling in a direction perpendicular to the electric field, and the magnetic field is also perpendicular to the direction of travel. So all three of them, they form a right-handed coordinate system, basically like this. So if this was the electric field, this is the magnetic field, this is direction of the propagation. So this is how the wave is moving. If an electron vibrates up and down 1,000 times each second. So in 1 second, it goes up and down 1,000 times. Okay. It generates an electromagnetic wave with a period of 1,000. No, the period is not actually 1,000 seconds, because in one oscillation, it's actually 0.01 second. That's the period, because it takes 1,000 of this to make 1 second. So each one of them must be a thousandth of a second. Its speed, no, that's not correct. The speed of the electromagnetic phase is always 300 million meters per second or 300,000 kilometers per second. Taken. The wavelength of 1,000 meters, we don't have the wavelength in here. We have only the frequency. The frequency is actually 1,000 times per second. So it's none of the above. So the frequency in here is actually equal to 1,000 hertz, okay? Or the period t is equal to this one, which is just the inverse of the frequency. So that's what was given in here. So this is the EM spectrum that I was talking about earlier. That what emerged from this one is the visible light is in this tiny region. Can I see this? I don't know if you see the picture in here or not. Let me see if I can make it bigger. Yeah, I like it better this way. It was too small for me to see anyway. So the visible light is in this region, as you can clearly see in here. This is the visible light. This is where our eyes are sensitive to. Anything higher in frequency is on this side. We don't see it. Anything lower in frequency is in this side, okay? You have the UV rays, ultraviolet radiation, you have the X-ray, and there is an overlap between all of this region. There is no clear point where you say, okay, this ends, the other one starts. And there is a gamma rays, but we know gamma rays is far more energetic than the X-rays, which are far more energetic than the UV radiation. But all of this can cause damage to the skin, at least UV to the skin, and the others actually to the inside of the organism. Then you have the infrared, which is shorter wavelength. Then you have the microwave. This is where your cell phone, and this is where your remote control actually. This is actually where your microwave oven. This is where actually telecommunication in general happens somewhere in this region, okay? So this is the frequency now is less and less, okay? It gets higher as you move in here to the gamma rays. The wavelengths get shorter actually. I mean, it gets longer this way and shorter this way. So when you go this way, it gets shorter, and in here it gets longer wavelength. So this is in a sense, the entire electromagnetic spectrum. It's a good idea to become at least knowledgeable about it and to see where the waves sit, okay? I explained how light is basically transmitted. In vacuum, you don't need anything. Light can move the way I described it. But inside materials, basically what happened in this case, each atom gets excited, and then once it's excited, it leaves its own ground state and then retransmits it again. So inside materials, light travels what appears to be slower than the speed of light. So you have an atom sitting in here, and you have another atom in here next to one another. So light ray comes in here, it's absorbed. So during that time when it's absorbed, there is no light traveling. Obviously, this atom goes into an excited state and then returns back to its ground state. When it does, it's going to emit the same light that it has received. Now, this one absorbs that light and goes excited. So during that time, light is not traveling. So in between atoms, light is traveling still with the speed 300,000 kilometers per second. But because it's being absorbed and re-emitted each time it interacts with the material, then in this case, it appears to be moving slower, okay? If it's transmitted completely through the material is actually transparent. If it's basically at the end is absorbed, so it's not going through, the material is opaque. And the materials can have all kinds of properties in here, depending on how they absorb and they emit light, okay? So this material is clearly transparent because light is absorbed. For a moment is basically the atom is excited, then the atom goes back to its ground state and re-emit that light. During that moment, the second atom is actually excited, and the other two atoms now are still in their ground state. Then this one will get rid of the frequency, the light that it has, the photon that is absorbed, basically, and goes back its ground state. Now this one is excited. It takes a little bit of time, and then it goes back to its ground state, and the light at the end comes out from the other side. So whatever sent the light from this side, the tree, for example, that went the light through it and gave that greenish color, is going to be transmitted with the same frequency at the end, and you will see the same image of what's going on through transparent material. Opaque material, though, no, it doesn't do that. Opaque material will absorb it, and basically, and that's it, okay? But transparent materials will transmit that. Now you have some materials that are opaque for frequencies and they're transparent for others, okay? For example, glass. Glass is actually a typical example where it absorbs transmits the visible light, and that's why we see stuff on the other side of the glass, and we use in our cars, we use it everywhere. But it's actually opaque, it absorbs the radiation of extreme high frequencies and also that of very low frequencies, namely long wavelength. So if this flower, for example, decides to go hot and re-emit, to go back to the ground, to its energy, re-emit that energy, but re-emits it in a longer wavelength, that longer wavelength is not going to go away. It's going to be trapped in this side. Again, I mentioned the fact that the speed of light is 300 million meters per second or 300,000 kilometers per second, because in the atmosphere and the air, there is not much interaction of light with the particles, with the atoms, so it travels mainly with the speed of light. But in water, for example, there is a denser structure in there, so light is being absorbed and emitted again, so it travels with 75% the speed of light. Glass is even slower, and diamond even slower, less than half the speed of light, less than 150,000 kilometers per second, for reasons that I explained above. Although these materials are still transparent. We have quite a few things, so I'm assuming that you guys can go through these discussions. Okay, opaque materials, I already mentioned that most things around us are opaque. They absorb light without re-emitting it. Okay, books, desks, the wall, and everything else that you have in there. Metals, they can be perfectly reflecting materials, and they're used actually in the mirrors, for example. There is a silver coating behind the mirror, behind the glass, so that you can see the reflection. Okay. Shadows formed basically from the different, or the lack of the different formations, because light goes around the objects. And in this case, either a large or far away source will produce light source will produce a sharp shadow, whereas if the nearby light source produces somewhat blurry image. And that has to do with the interference, now the fact that light is actually a wave. Okay. This is the same phenomenon. Now, this is how actually solar eclipses can happen, actually, how one of them goes in front of the other one. How we see light, how we see objects in general, it's because of a reflection, or of actually the light that hits the eye goes through a lens. This lens is made out of material that is that has a high index of refraction. Actually, the index of refraction is very close from that of the water. So the cornea in here will focus the rays to this point in here, to the lens. The lens now sends it to the eye. Now in the retina, there are some pieces in here where so there are some cones, and there are the I forgot the other ones, what they're called. I lost the word right now. Okay. One of them detects the intensity of the light, the other one detects the color of it, the frequency of it. Now, if the image forms right in here, and the image, because of the lens properties, is actually inverted. So if you're looking, for example, of an object upside up like this one, so the image that's going to be formed is going to be upside down. The brain, all of this information is collected and sent to the brain. The brain corrects the inversion and gives you the correct distance and the correct size, basically, of the object. So that is how the eye works. Sometimes there is a problem with the eye. Either this one is bulgy, or this one is too long, and the image forms before. So for a long eye, the image forms in here, okay? Or the opposite of that. So what you need in this case, you need lens in here, you need actually glasses in here to push, to help this lens in here push the image back into the retina. So that's why when you go to your eye doctor, he puts a lot of different glasses in here and asks you, how is the image? How is the image from 1 to 10? How does it look like? Until you come up with the best, basically, number in here to help the eye, in this case, focus the image right on the retina so that your brain can interpret a sharper image. Or it could be the other way around. It could be that the image actually is formed behind the retina. So what is finding in here is a very not focused image. So again, you use a diffracting lens in here to bring the image back outside so that it falls right on the retina. So this is how retina works. And there is a point in your eye, and you can actually experiment with this one. Close one eye and take an object and move it around, and don't look anywhere, don't move your eye. And at some point, that object will actually disappear on you and then reappear, okay? And that is actually the experiment you can do, or at least put your hand on one eye. Don't use glasses if you're going to do this one. You will find the blind spot in your eye, okay? As the object is moving, as the object is moving, at some point it's going to disappear completely, and I couldn't do it right now. I have to do it actually without the screen in front of me. You will see that there is the blind spot, because if the image happen in here, falls in here, well, there is no receptors in there, okay? So there is no image formed, so the brain loses track of the object, okay? And just right in the middle of the eye, somewhere in the middle of the eye. That is where the blind spot is. So that's why it's called the blind spot. So that's how the eye sees. Okay, here they are. Okay, there are rods and cones, okay? So the cones are the ones that detect the color, and the rods are detecting the intensity, how bright the object is or how light thereof, okay? And we detect motion. The eye itself is a fascinating device, honestly. And usually physics stops right at the retina. After that, what the brain does and how the colors are interpreted and how these things, for example, the illusions are happening, that is outside of physics. For example, it looks like these lines are tilted, but they are not. They're exactly parallel, just like this one, okay? And it looks like this line itself is not continuous, but it is a continuous line, okay? Looks like it's broken, but it is not. Same thing in here. So this thing in here, so wherever you focus, there is actually a white dot somewhere in there, because if you try to count how many black dots, you're going to miss them. So again, this has to do how the eye interprets things. Man, it's always fascinating to do these things in here, and it can be dizzying. Okay, so this is the chapter, the two chapters, 25, 26. I hope that you guys go through the reading from them, and there will be assignments related to these two chapters. And the discussion is not graded now for this assignment, for this chapters. So I will see you guys on Thursday. Any questions? Let me stop there. Do you have a question, general question, or just a?
Yeah, a question that you just said about the discussions. Just this chapter isn't going to be graded, or the following?
It's not graded. This chapter is not graded, so there might be some grades in down the road. You will know about them. Okay.
Okay.
Okay. Thank you.
Thank you.
Okay.